Alright, this video lesson is on adding vector quantities. So let's get right into it. When we add vector quantities, we produce something called a resultant vector. That resultant vector is kind of the sum of those two vectors. For example, when you add the numbers 1 and 2, the sum is 3. Vectors work very similarly. When you add vectors A and B, you produce what's called a resultant vector. When we've done this in the past, we've referred to the resultant vector as the net force. This is the only previous experience that we've had with adding vectors together. And the examples that we've worked with have been relatively simple. We've got several illustrated right here. When vectors are pointing in the same direction and they're added together, they add their magnitudes together. So for example, 5 plus 5 produces this 10 in magnitude here. And we also have recognized that when vectors are opposing each other, we see that they subtract, so to speak. When one vector is equal in magnitude to another vector, but they're in opposite directions, they balance out. Or in other words, our resultant vector is just 0. So that looks a little bit more familiar when we're looking at force diagrams. So for example, this first diagram has a 1200 Newton force vertically and an 800 Newton force vertically as well, but downwards. These two vectors sum to create a 400 Newton vector that's pointed upwards. So we've always called this resultant vector net force. And we have considered its magnitude with how many newtons it is, and we've also considered its direction as far as whether it's up or down or left or right. What we're going to start referring to now, or thinking about now, are vectors that add together that are not perfectly vertical or horizontal. We're going to start summing vectors that are diagonal. And the way that we're going to do this is with the tail-to-head method. So the tail-to-head method makes it very simple to add vectors the same way every time, regardless of how they're drawn. The idea is that your first step is connecting all of the vectors in the same manner. Tail connected to a head, tail connected to another head, so that you have a train of vectors all connected. Step 2, after you've connected all of the vectors, is to draw one resultant vector from the very beginning to the very end. So let's do an example of that together. We've got vectors A, B, and C here. If I wanted to add these three vectors up, I would have to connect them tail to head. So I'm going to remove these or move them somewhere where I've got more space. So if I wanted to start with vector A, I could start with vector A here. And if I wanted to connect vector C, for example, let's say, I would have to connect vector C's tail to the head of vector A. So it's very specific here that it's tail to head. And then I would connect vector B in the same manner. Vector B's tail to vector C's head. Now, the order that I add my vectors doesn't make a difference. So the fact that I added A and then C and then B won't make a difference from if I maybe went in the other direction. Maybe I start with B and I add A, and then from A I add C. I'm actually going to get the same resultant vector either way. And my resultant vector is going to come from drawing a vector connecting the very beginning tail to the very ending head. This would be my resultant vector. So your resultant vector is always going to connect the very beginning of your train of vectors to the very end of your train of vectors. So if I wanted to redraw this vector in a little bit more of a neat way, what I would do is I'd just pay attention to how large the vector is vertically and horizontally. And what I mean by that is that this resultant vector goes up 2 units and over 3 units. So I could redraw my resultant vector over here as long as I went up 2 units, over 3 units. Perfect, and that would be my resultant vector from the sum of these 3 vectors, A, B, and C. And again, regardless of what order you add them in, we would all get the same resultant vector that's up 2 units and over 3 units. So let's do one more example together. We've got 3 new vectors, and again, I'm just going to arrange them from tail to head so that I've got one complete train of vectors. So let's just start with vector A. Start with vector A here, I guess. I'm trying to make sure I've got enough room for all my vectors. And then let's start with vector B. Now you might be wondering, how am I picking the order in which I'm adding these vectors? I'm really just trying to add the vectors in such a way that they don't overlap too much. Sometimes it can get kind of messy if they overlap too much, so I just try to avoid that. So vector B is connected. Now I'm just going to connect vector C, tail to head, and now I've got a complete train of vectors. So my resultant vector is going to be the connection from the very beginning, the tail, to the very ending head. So this resultant vector is 1 unit to the left and 2 units down. So if I wanted to redraw it over here, it would be 1 unit to the left and 2 units down. So that's how you would draw the resultant vector, but we're going to start working with quantities specifically in regards to the resultant vector. We're going to need to be able to describe its magnitude as well as its direction. So let's get started with learning how to find the magnitude of resultant vectors. Now, when we're finding the magnitude of resultant vectors, our first step is actually one that we've been doing, finding the vertical and horizontal components. And I'm going to highlight where we've already done that. When we redrew our vectors, we paid attention to how far over and how far down we had to go over. These are the components of the vector. So how far to the left or right your vector moves or is pointed is your horizontal component. How far up or down your vector is pointed is your vertical component. So essentially we need to know how far over and how far up or down our vector goes. So that's the first step. Once we've found our components of our vector, the second step is using the Pythagorean theorem. Now you may have experience with the Pythagorean theorem, you might not. So we're going to do a little bit of review. The Pythagorean theorem is in regards to right triangles. Now, vectors are right triangles, and here's what I mean by that. If I were to make some annotations to this, let's say that the C length of this triangle was actually our resultant vector. The A side length is the horizontal component. This is how far over our vector goes. And the B component of our vector is how far up the vector goes. So the A and B side lengths of the right triangle are actually the same thing as our vertical and horizontal components of a resultant vector. So this formula of A squared plus B squared equals C squared is applicable to finding the magnitude of a vector. A squared is just your horizontal component, and B squared is your vertical component, and C squared is the magnitude or the length of your vector squared. So we're going to use the Pythagorean theorem for a couple of examples and try and find the magnitude of the resultant vector. So let's say that we were adding vectors A, B, and C together, and our resultant vector is pictured here. It's over to the right 3 and up 2. If I were to redraw this vector over here in this allotted space that I've got, I can see that it does make a right triangle. My side lengths are 3 and 2. My A side length, I'm just going to plug in 2 for A. My B side length, I'm just going to plug in 3 for B. And my resultant vector, my magnitude of my resultant vector is going to be my C side length. Now you might be wondering, why did I plug in 2 for A and why did I plug in 3 for B, because that doesn't quite match what we have up here. It actually doesn't make a difference which side length you plug in for A and B. You'll still get the same answer regardless. So I'm going to substitute in 2 for A, 3 for B, and C is just the magnitude of my vector, squared. So 2 squared is going to simplify to 4, 3 squared will simplify to 9, and this is equal to my magnitude squared. 4 plus 9 gets me 13, and this is equal to my magnitude squared. Now, I don't want the magnitude squared. I want just the magnitude of the vector. In other words, I want just the length of the vector. So to find the length of the vector, I'm going to square root both sides. And when I do that, I'm going to end up with the square root of 13 equals the magnitude of my vector. So hopefully we'll get some magnitudes that are whole numbers and aren't just square root values or quantities, but if not, that's fine too. So let's do one more example together. We've got a plus b plus c, and it kind of overlaps a little bit. This is kind of what I was referring to, where your resultant vector is going to kind of cut through your train, but that's okay. The resultant vector is really large. It's over 9 and up 3. So I'm going to plug in 9 for my a side length. I'm going to plug in 3 for my b side length, and c is the magnitude of my vector. So 9 squared is 81, 3 squared is 9, and this is equal to my magnitude squared. So 90 is going to equal my magnitude squared. I'm just going to square root both sides. And when I do that, my calculator will simplify this for me if I'm not sure if it'll simplify. So let's plug that in our calculator and see what the calculator simplifies it to. So if I did 90 square root, I could get a decimal, but some calculators do give a scientific answer. Regardless of how you present your answer, as long as it's accurate, it's okay. So I'll just use 9.4. I guess it actually rounds up to 9.5. So let's use 9.5 as the final magnitude of this vector. So the last one is a try, and I haven't actually drawn the resultant vector for you. So it's going to be your job to draw the resultant vector and then find the magnitude of that resultant vector. So go ahead and pause the video, and when you're ready to check your answer, go ahead and unpause. Alright, I'm going to assume that if you're watching this, you're ready to check your answer with this. So let's get started. I'm going to draw B first. I'm going to draw C connected to B, and again I'm doing tail to head. I want it to just line up with my coordinates really nicely, and then I'm going to connect B. I wonder if this would be better. That actually does look better. I think I'll do A first, then B, then C. That's going to give me a really nice resultant that doesn't overlap at all or cross through anything. Perfect. So here's my resultant vector. It's up 1 and over 1, 2, 3, 4, 5. So when I redraw this, I'm going to go over 5, up 1. Perfect. So 5 over, up 1. So when I plug into my Pythagorean theorem, I'll just plug in. Let's plug in 5 for A, and then let's plug in 1 for B, and then C is just going to be the magnitude of my vector. So now I can start substituting. 5 squared plus 1 squared is going to equal my magnitude squared. So this will simplify to 25 plus 1 equals r squared, which is 26 equals r squared. And I just take the square root, and I can leave this as the square root of 26, or I could simplify it in the calculator and do the square root of 26, and I'm going to get 5.1. So whether you write your answer as 5.1 or you just keep your answer under the square root, either answer is acceptable for your final answer for your magnitude. So that concludes our lesson on vector addition.